Hello and Assalamualaikum everyone. My name is Muhammad Afan Mumin and today I will be presenting my poster titled Modeling Population Growth Using Mathematica. This project explores how differential equations can describe and predict population dynamics, a fundamental concept in ecology, economics, and epidemiology. Next, we move on to introduction. Population growth is an essential process in nature and society. Understanding it helps us manage resources, forecast trends, and study environmental impacts. Differential equations provide a mathematical framework to model how population change over time. Next, problem statement and literature review. Traditionally, population growth was modeled using the exponential equation, which assumes unlimited resources. However, Pierre Verhulst introduced the logistic model in 1838, which accounts for limited resources through a carrying capacity. This model remains widely used in modern ecological studies. Next, we move on to methodology. The logistic growth equation is given by dp over dt equals to rp in bracket 1 minus p over k, where pt is population at time t, r is growth rate, and k is the carrying capacity. So let's move on to computational solution. Using Mathematica, I solve and visualize this equation numerically. Let's look at how we use Mathematica to solve the logistic growth equation. I want to highlight this every single three line in this code I use. So the first line is the parameter. Here I define it r equal to 0.5, which is the growth rate. K is 1000, which is the carrying capacity. P naught is 50, is aka the initial population at the time of 0. Um, let's go to line 2. Line 2 here, um, this line uses and dissolve Mathematical's numerical solver. So the first part here, that I highlight here is the logistic differential equation. This part sets the initial condition. P is the function we want to solve for. And lastly, this part tells Mathematica to compute the solution from time 0 to 20. So the last line is plotting the solution. We want to plot the solution, so this line we substitute the solution into pt. So this one I highlight sets the time range for the plot. Plot label and axis label make appear the legend in the graph to make the graph look professional and clear. So the resulting graph shows rapid initial growth that gradually stabilizes near the carrying capacity. So let's move on into discussion. From the plot, we can see that the population grows quickly at first, but slows as it nears k. This behavior contrasts with exponential growth, which continues indefinitely. The logistic model is more realistic for biological and social systems. So the conclusion is the Mathematica provides a powerful environment for solving and visualizing differential equations. Through this project, we gain insight into how mathematical models can explain real-world phenomena like population dynamics. So my key reference is includes Verhulst's original work from 1838. Second is Wolfram documentation to show the graph there. And then Lastly, I use recent ecological study. Mm, that's all. Thank you for watching. I hope this presentation helps you appreciate how mathematics and computation come together to model life itself.